Definition. An isomorphism from a group G to itself is called an automorphism of G. For example, the function phi from the complex number set C to itself, given by phi of A plus bi equals A minus bi, is an automorphism of the group of the complex numbers under addition. If we restrict phi to C star, the set of all non-zero complex numbers, C star is a group with respect to multiplication, and the restriction of phi on that group is an automorphism of C star. Definition. An inner automorphism induced by an element A. Let G be a group and let A be an element in G. The function phi sub A, defined by phi sub A of x equals A times x times A to the negative 1, for all x in G, is called an inner automorphism of G induced by A. Of course, if the group G is abelian, it is commutative, then here you can move x on the other side until you get phi of x, phi sub A of x equals x, which is the identity map. So it's a trivial isomorphism in that case. So it is interesting only when the group G is not abelian. If G is a group, we use this out of G to denote the set of all automorphisms of G, and in G to denote the set of all inner automorphisms of G. Theorem 6.4, these two sets are groups under the operation composition of maps. Our goal now is to determine the automorphism group of Z10. You know the group Z10 consists of all integers from 0 to 9, and the operation of the group is addition mod 10. Because Z10 is so simple, we can compute all automorphisms easily. We observe that if alpha is an automorphism of Z10, it is enough to know alpha of 1 to know alpha of k for any integer k. It is the case because alpha of k is alpha of 1 plus 1 plus 1 k times, but because alpha is automorphism, it respects the operation. That means alpha can go inside where the ones are and to add those. But this means that because all terms are equal, we have k times alpha of 1. But alpha 1 is known, so we know what is k times alpha 1. So we need only determine the choices for alpha 1 that make alpha an automorphism of Z10. property 5 of theorem 6.2 tells us that alpha of 1, the order of alpha 1 must be equal to the order of 1, and therefore the order of 1 in this group is 10 because 1 is a generator. So alpha of 1 must be a generator of Z10, and Z10 has only 4 generators. These are the numbers from 1 to 9 that are relatively prime to 10, as we know. So those numbers are 1, 3, 7, and 9. And these choices determine the map alpha. So if alpha of 1 is 1, we denote that name by alpha 1. This is the identity map, and it is an automorphism of Z10. If alpha of 1 is 3, we denote this map by alpha 3. It is a map for now. We'll prove that it is an automorphism later. And alpha 7 and alpha 9 are defined similarly. So the only possibilities for automorphisms are these 4 maps. Alpha 1 is the identity map, so it is the trivial automorphism. Let's check alpha 3. Since x mod 10 is equal to y mod 10, this equality implies 3x mod 10 equals 3y mod 10. Yeah, those remainders are also equal. This means that alpha 3 is well defined. This is needed here if we allow numbers bigger than 10. If we look only for the integers from 0 to 9, we don't need this. So alpha 3 is well defined in that sense. Because alpha 3 of 1 is 3, and 3 is a generator of Z10, it follows that alpha 3 is on 2. All multiples of 3 will be images, and the multiples of 3 form all the group Z10. 3 is a generator, as we know. Finally, alpha 3 of A plus B is 3 times A plus B, and this is 3A plus 3B from the distributive law, which is alpha 3 of A plus alpha 3 of B. So alpha 3 is operation preserving, so alpha 3 is an automorphism of Z10. Similarly, we can prove that alpha 7 and alpha 9 are also automorphisms. So we know that the automorphism group of Z10 consists of these 4 automorphisms: alpha 1, alpha 3, alpha 7, and alpha 9. What is the structure of the group? What is alpha 3 times alpha 3? This is the composition of the maps, and if you apply the composition to 1, alpha 3 acts first, 1 goes to 3, and then the next alpha 3 acts, 3 goes to 3 times 3, because alpha 3 acts like that. Each number is multiplied by 3. So it is 9, which means that it is the same as alpha 9 of 1. So because any automorphism is completely determined by the image of 1 in this group, this means that alpha 3, the composition is equal to alpha 9. Similarly, alpha 3 cubed is alpha with index 7. Why is that? You multiply 3 times 3 times 3 and take the remainder mod 10. 3 times 3 times 3 is 81 mod 3 times 3 cubed is 27, mod 10 it is 7. So alpha 3 cubed is alpha 7, and alpha 3 to the 4 is 3 to the 4 mod 10 is 1, so it is alpha 1. So the order of alpha 3 in the automorphism group is 4, and 4 is the order of the group. We have 4 automorphisms here. This means that the group of all automorphisms of Z10 is cyclic. It is generated by alpha 3. We also know that alpha 3 times alpha 7 is alpha with index 3 times 7 mod 10. 21 mod 10 is 1. So we can fill out this table for the operations in Z10, and we see that we handle the indexes how? We multiply them and take the remainder mod 10. But in the group U10, which consists of all integers from 1 to 9 relatively prime to 10, that is, it consists of 1, 3, 7, and 9, just the indexes that we had here. And the operation in this group is multiplication mod 10. We have a bijection from U10 to the automorphism group that sends 1 to alpha 1, 3 to alpha 3, 7 to alpha 7, and 9 to alpha 9. And it sends the multiplication table of U10 to this operational table of the automorphism group of Z10. So the automorphism group of Z10 is isomorphic to the group U10. Similarly, in theorem 6.5, one can prove that the automorphism group of Zn for any positive integer n is isomorphic to the group Un that we know.